presentation and just see whether you can see that it turns itself into there it is on the big presentation now. Is that visible?
Yep. Can you hit like F5 and make it full screen?
I've just made it full screen, and
there it is. Perfect. Perfect.
There's a little delay from South Africa, I think.
Well, it's uphill towards you guys.
Yeah.
All right, Fred.
Okay, guys. I've got it, and I'm going to try and talk you through this. It's quite an experience on this end, but I presume you guys are already now fully au fait with all that's going on, so bear with me and let's go. I'm going to continue, and I hear what I presume you can interrupt me as we go down.
Sounds good, Fred.
Okay, are you seeing the global picture of where we're talking about?
Still the first screen. There we go.
It looks like there's about a 3-second display, or a delay. There's about a 3-second delay.
Okay, I'll work on that, and the 3-second delay I'll try and catch up. But what you're seeing now is a global picture, and stop me if you want to at any time. And must I talk slower, or can I continue talking in normal manner?
I think
the normal.
Okay. What I can see, what I want to show to you is that we're talking about both the US, Europe, China, and Africa, but we're going to concentrate primarily on Europe and China. You will also see that there are symbols to reflect the small machine in orange if they are on your side, the same color, and you'll see the big oblong green ones, which are the big machine instead of the circles. So there have been applications, and there are places where they're seated. So in China there will be 2 big machines, and Europe there is 1 big machine at the moment, and the second big machine is being finally manufactured. So we're talking in China and 1 in Switzerland, and I'll talk more about that. Let me just check whether you followed that through, and then I'm going to try and pace myself to make sure that I get through what I want to say.
I think we're good, Fred. Okay,
I'm going to continue. Now, we're talking about 3 types of machines, so I'm going to cover them. The MMLS 66, which is the long, tall machine which has 6 axles to it. The MMLS 10 has 4 axles to it, and both of those 2 machines can take dual wheels and or super singles. The small machine is well known to you guys, and you will see the reason for talking to that together with the big machines in a short while. But it has the 4 axles similar to the MMLS 10. It's just 1/3 scale, and they're all mobile. Now, if we just look at the response, and I'm not going to discuss details about the machines at all. Those can be checked if and when anybody wishes to do that. And I saw some of the names. Perhaps I can just stop for a minute and ask. I know Buzz is there, and I thought I saw Ben Worrell, but I don't know who else is on the line. Can I just get a feel?
Yeah, I'll answer that, Fred. We've got Andy Geezy and Ben and Eel and Tim Klein.
Good. Thanks a lot. Now, what you'll see over here are just the attributes, and the reason for talking about that is that when we talk about how we apply the machine, or how the teams have applied it, and I'm not really talking in personal capacity, I'm talking about the teams at the moment, you can have a varied test length, which can be either 4.2 meters or 3 meters added to that, just over 7 meters, or on the small machine at 1 meter. The lateral movements can be 500 millimeters, that is 1/2 meter left and 1/2 meter right. The speed frequency can go down to about 8 kilometers an hour and can go up to 22 kilometers an hour. Tire pressures can be taken up to 1,000 kilopascal, or you can go down as low as 500 or 480. The tire tread you can vary, and the load amplitude can be taken up to 75 kilonewton on the half axle. Just say that slowly again, 75 kilonewton, and you can take it down to 40 kilonewton on a half axle, and you've got the super and the dual tire. We now go on. The tests that have been conducted successfully in Europe are 3 block pavement tests in Switzerland, 1 block pavement test in Austria, and several hot mix asphalt, full depth asphalt pavements in Switzerland. These tests have been conducted over the last 2 years, starting in about 2009. Some tests were done earlier, but 2009, 2010, and just moving into 2011. The tests.
What do you mean by block pavement tests?
Say again?
What do you mean by block pavement?
Block pavements are what you guys, I'm not sure what the terminology is, but block pavements to us would be the small paving, the pavers. I think you call them pavers.
Okay.
Is that clear? In other words, it's a paver block of different shapes and sizes, and there are now new models on the market which either can be porous or they can be solid. You can change the shape of it, and you can construct them in different manners, and you can also change the thickness.
Okay.
They're very popular on airports, and they're very, very popular on some of the European highways and down in Australia as well, and down in South Africa. So those block pavements were tested, and I'll talk subsequently. I'm not going to give you any feedback on the tests of those today, but there will be a paper if it's accepted. There has been a paper submitted to the international conference from Austria, and they completed, I believe, 7 different tests of different configurations, and without going into the details, they had them paved, checked, and they're doing some design work, some design analysis, some in-depth evaluation of the design codes and the likes of it with those tests. And those tests have the first phase has been completed, and it will be reported accordingly at the international conference. The Swiss tests were done in different environmental conditions, that is very cold conditions and also hot conditions. They were more comprehensive than the Austrians, but the Austrians were more focused on specific types of tests on one locality. Going on to the pictures, and here you see a picture of a super single that had been trafficked on one of the pavements in Austria. Is that coming across clearly?
Yes.
Good. And you can see they're doing some rut evaluation, and they do this by either using a profilometer, which is available, or just doing by straight edge, depending on what the purpose is. And this is one of the patterns that they had tested. This is a typical cold condition that was tested in Switzerland. You see the conditions without having to explain it, but it's the MLS 10 parked on top of the paving blocks, and you can see that it's quite chilly over there. This is another picture of the MLS 10 when it was doing the full calibration testing, also in Switzerland, near Zurich, and also under cold conditions, and you can see that dates back to October 2008. So it is an old picture, but the one I just showed you a minute ago, this one is a much more recent one. It was just done at the end of last year. Now, if you look underneath here, this is what you would see, and I'm not going to waste time. I can subsequently call up a video, but what you can see over here is the super single running on the block paving. Now, 3 successful MLS 6 tests were done in China. And the 3 tests are cited over here. And I just want to ask one question. On my screen, part of it is blurred with the status of what I'm doing and the webcam and so on. Do you see the full screen, or is that also on your screen?
We see at least here, I see a full slide with 3 bullet points on it. But that's
okay, that's great.
I don't see anything else.
That's great. Now the first one that we'll be discussing are 3 successful MMLS-66 tests in China, where we've got bridge deck surfacing in the Liaoning province, which is in the northeast, and that I will be discussing in some detail, but most of the detail will probably feature in what I'm going to talk about in case studies that are going to be reported at the international conference. But the bridge deck surfacing I'll talk about, and that was in Liaoning province. In the laboratory, and I'll show you a picture of the facility and how it was set up. Then there was a test out in Nanzamu, which is out about 200 kilometers from the capital city of the province, and it had some regular AC and rubber asphalt pavement testing for comparison purposes on 2 types of pavements, and we'll talk about that in a short while. Then we're going to get to full depth asphalt pavements on sand subgrade that was tested on an island close to Shanghai, or in the outskirts of Shanghai, with a water table that had varied and with a sand subgrade. So they were doing tests on full depth pavement with changing in the subgrade conditions on the Chongming Island in China, close to Shanghai. So those are the 3 primary tests that were conducted in China. Now, to get a bit of a feel, this is the MMLS-66 on its way off to China, being loaded onto a ship, and you see it driving up into the hull of the ship, one of my engineers up front is actually doing remote control to drive the machine up into the ship. This is now inside the laboratory, and I've got a video clip of this, which I didn't have an opportunity of linking, and I was just a bit worried that I'm going to rather keep it separate. So when we go through, I'll at the end just slide through to the video clip, and without disturbing our presentation now, but I'll show you maneuvering just while I'm talking about it. This is the laboratory at Liaoning, their in-house laboratory, and you see a person on the far right in the back. He's got the remote control in his hand, and he's driving the machine now and parking it in a position where they're going to do tests with it. This is just another shot of the same movement, and where we're driving over here was subsequently where the bridge was constructed, and I'll show you some pictures of the bridge construction itself. The bridge construction is a steel deck, but we'll talk about that in a short moment. This is a picture, a close-up picture of the machine running with the wheel coming towards us. But what is also interesting is the video clip, one of the video clips, I'm not sure which one it is, but that's not important, was taken by the Swiss television station, and they had a whole program on television on the way in which they address the testing on highways, how they select the sites and discuss the decay, or for that matter the need to do maintenance and the likes of it as a public exercise. And that was a video clip that was on the internet, available for downloading and for looking at for the general public. Now here we're inside the laboratory again, and you can see on the left hand side the video screen here, or the monitor, and then you also see on what would be my right, and if you're looking at the picture on your right, the machine is lifted up about 1 meter up in height, and we're sitting on the bridge deck, and the bridge deck is supported on the far end, and it's got 2 channel sections spanning across to represent two of the bridge structural components which carry between them then the surface deck that had to be decked with asphalt. And here we're sitting on top of the asphalt, and you can see the duals have run along here, and they've got the asphalt along the length of the section, which is in on the 6.6 meter machine, or for that matter 6.6 trafficking. It actually extends up to 7.6, but the trafficking section that we work on is then the 6.6. Now, if you go under the machine once again, you see over here heating units on the right-hand side. You can see the top deck heating unit, and you can see some of the heating elements in orange. And then if you look down on the left-hand side, which is on the same slide, you can see the wheel suspended. So the machine is lifted up into the air here, and it is shining on the bottom where the pavement is, and you can see on the left and right-hand side of the, I might just use a mouse if I can. Can you see the mouse moving the arrow over there on the light section?
We can see that, yes.
Now, if you move across there, you'll see on the left-hand side and on the right-hand side are the heating elements for the pavement, which are beside the wheel, where the wheel is over there. So you've got the upper ones. If I move up to the top right, you can see the lights on the top over here with the reflecting heat units, and on the bottom you see pavement heating units on the floor. Now, when you're channeling, then there's no problem. You've got the heating units from the top and the bottom all stationary. When you are doing lateral wander, these bottom ones are moved laterally apart slightly, because the top one has the ability to spread and reach them where they are, so then you have the machine moving transversely back and forth. If we go on at the close shot, this is a shot that was taken on the island highway, where they also had heating units on the pavement, and I'll cover the intent perhaps slightly more now if it doesn't muddle your thoughts. The pavement on the island was a full depth pavement, something in the order of 200 millimeters of asphalt, supported by 2 layers of cement treated asphalt, gravel, supported by further cement treated sand, and then supported by the sand subgrade. So a very stiff pavement. And on the top surface they were heating the asphalt to check what the change in stiffness would be, the effect on the pavement structure below, and the varying water table. We'll talk about that slightly more when we get to the case study in more detail, but this is the surface that you're looking at, the asphalt, where it was running in a channelized mode. Now if we move to the CRILP, which is the Communication Research Institute of Liaoning Province, this is in Nanzamu, the one I referred to as the test section of the highway. We've just touched base on the bridge now. Now we're going out into the field, and what the situation here was that they had downloaded, put about something in the order of 5 million load applications, 75 kilonewton down onto this, onto 2 sections over there. And we're looking at the 2 sections along, straddled alongside, or rather head to head on the slide we're looking at. The right-hand side is just a screen for protection for wind and the likes of it, but on the rear end is the office of the campus. Next to the machine is also the lateral movement system, just placed alongside, but when they're functioning, I'll show you a picture how they function in a short while. Now, here you see another view of the same scene, just from the other end, and you see some of the staff over there and some of the management office, and you can get a bit of a feel of that part of the country. There are many flat parts and, of course, mountain and hilly sides as well, and this is in the mountainous area on one of the that goes where the new highway is going to go, and this is on a section of that new highway. Now, if we bring the machine right back to the laboratory, the central laboratory in Shenyang, this is a picture of the machine itself parked on several sections which they've constructed next to each other. And you can see them standing over here. There's an operator here on my bottom left, and you can see the definition of the section in Chinese over there. And there are 1, 2, 3, 4 of these sections next to each other, and you've got a screen over there for protection against the environment, but also to limit noise from the built-up area, which is not far from the close proximity here. Other than that, not much more to say except to say the front part of the machine, which is just in front of the individual standing there, is really the section where the control systems are. Just where my arrow is going to show, that's the operational area if you want to do it manually. Otherwise, he's doing it by hand. And the rear end, you see the power source, which can either be online or can be a generator on the machine. Now, if we look at the trafficking at Nanzamu, which I just spoke about, that what they had is 2 sections over there. The one section was a wrap section, that is rubber asphalt, and the other one was a regular conventional asphalt, as we know it, concrete, AC. And what you can see over here is the way in which it's performed. I mentioned the order of magnitude of the loads they put on, and this is something in the order of just after 1 million of these load applications had gone down, and they are strain gauged and pressure gauged and a lot to pick up some response of the pavement itself below. If we move across to the laboratory in Shanghai, this is the MMLS 66 of Tongji University. And you can see here, once again, the control unit, and you can see the machine is now set up to do lateral wander, and it's sitting on a pedestal on both ends, 2 pedestals, and it moves laterally 500 millimeters one way and 500 millimeters the other way. It's sitting on the pavement section now in a testing mode, and if you want to lift the machine, then you can lift the whole machine up by these hydraulic jacks, which I'm indicating now. And once again, you see the control unit on the left, and you can see the vents at the top, which actually circulate air inside the system to control heat flow and control and equalize the temperature inside. The doors, which are brown over here, are actually windows that you can look through and access if need be. And that's about it on this slide. You can see we're inside their APT laboratory. They've got a test bed, which is 60 meters long and 20 meters wide and 2 meters deep, where they can construct full depth pavements. And you can control the water level in it depending on what your choice is. And then if we look at the other side, we're looking to the rear of the machine in this parked position. And here you can see the machine being moved by the hydraulic cylinders, which are protruding from the side of the machine. And you can also see the power cables that are going to the rear end where the power is coming from, but this is now fed by line feed. And you can see cranes at the top where you can maneuver. And you see at the far end, you can also look at the test pit, which is still not occupied at this position. And just going next slide, this is just another slide of the same system, just further apart, just to show the action. Okay, now, as I've already mentioned to you, and I just want to keep my eye on the watch, I see the time has moved on rapidly, we're going to look at the study. The reports are going to be submitted to the Sacramento APT, and there are going to be several of these submitted either in format from Switzerland or from Austria or from China itself. Now, the 4 studies are the bridge deck one, the APT rubber, the filtering one in Switzerland, which is really the full depth pavement, and then the pavement in China on the island. I'm just going to be brief because I am not really clearly at liberty to give all of the findings or for the particular details because of the papers that have been submitted. I will come to some that are going to report back on the CAPSA conference that's just been done in South Africa. The performance between the two pavements on the bridge were successfully evaluated. The performance was successfully evaluated to differentiate as to which one is the more beneficial for the condition of what they were looking for. They were selecting what would provide waterproofing, what would provide prevention against slipping and sliding, and what would in fact do have minimal rutting. And they were able to differentiate between those, so they found it a successful application. The one at Nanzamu was the APT performance of two pavements in terms of structural composition and construction features, and the information was found to be useful, and using it for design purposes because the two pavements were different in structural composition and in material composition. So they were experiencing the application of new material, which you would know as goose asphalt, and then evaluating how to deal with that and what are the constraints in actually constructing with that material, and comparing that to the pavement performance of their conventional pavements. And I've given you some sort of an inkling as to what their types of pavements are. Full depth in many instances, cement-treated materials, and one of the things they're looking at carefully is how to handle cement-treated materials beneficially and not to get into too much of a trouble with reflection cracking. Now, case study number 3 was the comparison of APT response in terms of strains in full depth asphalt and under the MMLS 3. Now, it was interesting that the application of what was done, and this is a test that was done in Switzerland, where they had fully instrumented full depth pavement, I think 190 millimeters asphalt on 2 layers of cement treated materials, and they had strain gauges in, and the test exercise in this instance was really to evaluate what the strains are under the full-scale machine and what they are under the small machine, and how they relate to each other in terms of what you calculate as the strains in elastic mode, and not elastoplastic, but just in plain linear elastic, and to check those and compare them between the machine and the response that they get in terms of strain, whether it is the big machine or the small machine, depending on what the strains are. And in fact, this was the prime purpose of doing this, and it's interesting that what they did is, and I omitted to put a slide in it, but let me interrupt myself and say that this publication is also in Spanish. They provided a paper in Argentina on some of the initial findings, and I can give the reference to those if they want to look at that. And there was also a German publication before putting the final paper together and putting a submission in now and for further publication of the findings. But what I'm interrupted myself in saying is that what they did is they extracted a full slab from the pavement. So what they did is they actually excavated the full 200 or 190 millimeters of asphalt by sawing it right through and removing the block of asphalt and taking that into the lab with the strain gauges intact, and then taking it into the lab and reconnecting, reconditioning, and doing strain tests in the laboratory under the MMLS, and comparing those as I've just indicated a short moment ago. So essentially the purpose was to see how compatible these items are and whether they are reasonable and representative of what they expected. And in fact, if I can just conclude on that, they concluded that it was compatible, the indicators in terms of both temperature and load frequency as primary test variables were totally compatible, and it was very interesting to see what sort of results they were finding in terms of transverse and longitudinal strains both in terms of the small machine and the big machine, which had different conditions, because the big machine had duals running, and they were measuring the strains between the duals. And the small machine had the strain gauge under the wheel. So you had different conditions, but you could check those conditions and you can do those calculations as you see fit. And that was gratifying for the team that was doing the research work, that this was not only compatible, but in fact very reasonable as indicators for the performance. And I think that in future one is likely to see more research work and perhaps more application of such ways of actually doing the APT testing. In the case study number 4, synthesis was done in the analysis of finding of the field and in the laboratory, also again under the MLS and MMLS, there's a typo over there, and the MLS 66. And the purpose of this was, as I'd indicated earlier on, is to actually see how the pavement responds as to where the damage and the failure mechanisms, or for that matter, distress occurs in the pavement structure as you go down the pavement structure from the thick asphalt to the cement-treated materials to the cement, that is the cement aggregate, and then cemented sand, and then a plain river sand that had not been used in pavement structures at all. And they had a water table in the island where the water table rose up to the level into the sand subgrade, and in fact then they had the superstructure, but they had 2 layers of sand in different parts of the test area. So they had a difference in thickness of the sand, and the rest of the pavement structure was similar. And then they heated the pavement and they tested at ambient temperature running about 25 to 30 to 35 max, and the heated temperatures running up to 40, 45, and in fact up to 55. And then they, in the laboratory, did testing with the MMLS, which took them in temperatures from 55 to 65, which in a way was somewhat of a frustration, because you had a different temperature now for the model machine rather than the full scale. But that was, one could surmount by doing the analysis and checking what the features are of the performance, and that was in fact done, and due regard for the temperature differences was considered. Once again, it is important to perhaps just go back to case study number 3, if I may, and just say that in those conditions you see that the temperature and the load frequency was varied. So there was a slow test and a fast test. And I'm going to come back to that statement because at the moment there is a very strong signal that is coming out, is that when one is testing, you've got to take into account the load frequency, which is obviously not new to you guys, but what is important is that when one is doing that and you're interpreting the results, you've got to put horses for courses, and you've got to take that into account, both in terms of distress and performance prediction. Now, if I go back to this case study number 4, what I can say to you is that, in fact, it was a situation that they had compatibility, and they found that the rutting primarily occurred, if not 95%, if more, was only due to the heating on the surface and no reflection from the water table variation or the sand consolidation or anything like that. So the pavement was doing all the work on the upper layers, and which one has spoken to each other many a time about. A lot of the distress is actually occurring in the top layer. So there's a lot of that in the paper itself. Conclusions, generally speaking, the peak-to-peak analysis of rutting was looking at the upward and the downward rut, and the small machine was only looking at the downward rutting. And there was compatibility between downward rutting, but if you take peak-to-peak and you start making analysis and trying to do predictions, you've got to take that into account. So this is discussed in more detail in there's a paper on the full-scale machine, and there's a paper on doing the interpretation of the rutting comparing small and big machine as well, two separate ways of looking at the final results. And the performance prediction was found plausible, provided one takes into account that what the effect is of the heat in the system. Something which is important, and I would share with you, is that one is looking more and more at the rates of deformation rather than just the total ruts. And the rates of deformation are discussed in some detail in these studies as well. Now, overall conclusions are that peak-to-peak perhaps needs to be looked at slightly more carefully in the future because it reflects the performance of the material itself. The rate of rutting is an important parameter as well, and the compatibility between these two APT devices was found to be reasonable and useful as gaining insight cost-effectively. Now, this is known to you. I'm not just showing it to you just for one reason. You know the small machine, but this is when it was actually used to measure the footprint tire pressures, and there's a full report available on the system that was used to classify the contact stresses under the wheels, both of the small machine and the big machine, and that information is available so that one knows what sort of stresses you're talking about. Now, I'm going to slip through this and just go, if you'll allow me to slide down a little bit and get more particularly to what I want to talk about now, about the CAPSA paper. I can just say that if I can interrupt my own thoughts, I'm seeing a picture here which I can reflect and tell you about. On the right-hand side of the picture, you can see the strain gauge as it was installed under the machine in Switzerland, longitudinally and transversely, and you can see some of the monitoring, and that same strain gauge was then the one that was intact in the block that was taken out. If we go down further, and I hope I'm going to get what I'm looking for, bear with me just a minute. Here, incidentally, is the picture of taking out the block, landed in this slide, and you can see the block being lifted in the air. I'm just slipping over this, and this is just showing the condition of the pavement and looking at some of the diagnostics. And now I'm going to look at a paper that was presented at CAPSA with 4 case studies that is of interest in the closure of our session, as we're going to report back on real trafficking full scale in terms of trucks, aircraft, and the MMLS again. And you'll see that there's a protocol that's been published on the application of the MMLS, and that is also to be found on the web. But what is important are 2 things over here in green and red. The one is the load frequency, and the other one is temperature. And there's a very, very important facet that needs to be taken into consideration if you're testing what we consider as harsh conditions. And here are 4 harsh condition cases which you will be able to get on the CAPSA website. But it's one in the Western Cape, where there's a mountain pass, in KwaZulu-Natal, which is on the east side in the hot part of the country, more like Miami, but in mountains. And then the Gauteng, which is a test between the HVS and the APT machine, the MMLS, the 2 machines next to each other to look at rutting rate. And then there were some tests done on Dubai Airport and in Australia, and also using the MMLS to do predictions. So let's look at this. There was clear evidence of the slow testing that is necessary to simulate heavy traffic and high temperatures. Then another finding, and I'm going over those findings in case we get caught in not having enough time to continue. The MMLS and the HVS rutting trends in terms of rate of rutting under similar conditions were fully compatible. The ability to scale the MMLS HMA field and laboratory performance to actual field rut performance as per this protocol was confirmed. And these are all set out in detail in the paper. Then what we've got is...
Fred, the rutting comparison between MMLS and HVS, was that structural rutting or more mix-related type rutting?
It is, thank you for the question, it is deformation under the heat, in other words, compaction, consolidation, and shear failure or shear movement. And to answer your question more specifically, the rut itself was in terms of the rutting rate. So in other words, once it had consolidated into what one would term as your second phase, there is a detailed rutting rate curve where one can compare same temperature, same velocity or frequency as to whether they've got the same rate of deformation. I don't know whether that answers your question.
Thank you.
No problem. Now, noteworthy is some important things that people sometimes preach. Change the grading and fix the rutting performance. It doesn't always work, and we've shown how that is affected. And the question as to where you are with modified and conventional binders and what the limits of these two are were proven in both cases with the big machine and the small machine, and similar results. And then looking at the application of different binders is also important, but what is really important is what I want to share with you is the top item number 4. The top test of the machine with the big machine is 6,000 load applications per hour. The speed of the small machine can vary 7,200 down to 1,800 per hour. So you can go with the big machine also slow if you want to, but many people are normally just running at the full speed, which is at 22 kilometers an hour. Now each of these has a place where it needs to be applied, and I'm just going to step over that for the moment. Let me say that what you'll see over here, and I think I might be caught with time, keeping my eye on the watch, just to show you the Western Cape, there were things that gave them a problem within the first season. They had rut up to 10 millimeters of rut, and the question was why. Had it been tested, and what you'll see over here is it was tested with 7,200 load applications per hour, and they had 1.67 millimeters of rut after 100,000 load applications. Now, when they changed the mix and developed a new mix with an EVA binder, the rut came down to 1.4 millimeters, but at the speed of 1/3 of the full speed. So that is now lying as intact, and the problem has been solved of the rutting. Now, I think this says for itself what I've just mentioned to you. I'm going to go on to the second one, which is in Durban. And here there was the question as to decide whether it should be an API or AP1 or an AE2 binder that they should use. It's very, very heavily trafficked, that section, heavy trucks, hilly country, and they used MMLS, the Hamburg test. They had flexural beam testing to check the fatigue, and there's a full report paper at CAPSA on all of this, but the purpose of this discussion was just to look at which machine, how did you differentiate whether it would be sufficiently stable under those conditions. And in fact, it proved that the two binders, the elastomer and the plastomer, they were able to make a decision on that, and they looked at Bailey mixes, they looked at the client's envelope, and they ultimately concluded that the AE2 binder had a rut depth of 2.5 millimeters compared to the other one, which had a much smaller rut, and they had no question as to which one to select for the purpose of the application. I'm not going to dwell on that any further at the moment. These are some of the rut results which would come out of a fast test or a slow test, and you can see how fine-tuned you can have to go with your measurements. Just on an interesting slide which I'm going to step over to and slide through has come to look at what happens when you've got gradients in the mountains and where are your ruts are going to occur. And we found that there was no correlation between maximum gradient and maximum ruts. However, it was interesting to note that the maximum rut values manifested in sections just prior to reaching the maximum gradient. So let me explain what that means. Is if you look at this, the peaks you see over here on this slide, you can see just before you get to the peaks, you can see where the maximum ruts are. And that's when there are cross gradients where the trucks are swaying left and right and they are pushing sideways, and it's very interesting to see either when you're going downhill or uphill, when you change there's a particular point where you can expect more ruts to occur, just as a way of interesting information coming through, not really trivia. This is the test report on the HVS MLS testing, and I'm going to say that provided temperature, load frequency, and the likes are all similar, you can really start looking at similar results. And I'm going to move, this is the setup. You see the small machine and the HVS standing behind it, and just moving on to the site where you look along the length. And if you, this is a very busy slide, but what I can say to you is that they tried to get a rut-resistant mix, and one was the conventionals, and they had some mixes that were performing good on a rolling country, flat country, compared to the hill country, and it was apparent that they had to look at the slower moving tests and the rutting rate. I'm sliding through these and giving you some information which is not necessarily important at the moment, just looking at facets of trafficking and the likes of it, which is not the debate now. But let me show you some of the curves. This is what I meant by when you're looking at the upward heave and the downward rutting. What we know of is now that we're basically looking at this part of it and forgetting about that part of it. And this is something we've got to look at perhaps more carefully, because that gives you another insight into the performance. Here you see some of the curves, and I'm just going to go over them very quickly. You'll see the green one over there is the HVS, and you can see this purple one over here is a laboratory MMLS, and you can also see this is a so-called rut-resistant mix, this one over here, this orange, and then you can see if you take the speed up, you can see you're immediately getting a much flatter curve as for your rutting at different temperatures over here. So that is just in a nutshell what I was trying to say over there, and this is just another picture of it. Once again, looking at rut rates and comparing them at under different thicknesses of asphalt. And you can see HVS 60 millimeters, HVS 25. So we were looking at the influence of that, and we were able to define that there is a change depending on the layer thickness in the ultimate rutting performance. The last one, which I'm going to touch on very quickly, is an airport in Dubai. And this is the familiar wheel loading and a very heavy 777. And if we look at this, we found it viable to use this, and Steve Emery from Australia used this, and he adopted the system that was discussed in great detail in the Transportation Journal in 2003 by Amy and co-authors in great detail, so we don't have to discuss that now, but to show to you that's what you do in the end. You put the picture together by looking at the stresses in each of these layers and looking at how each of the cores in those level layers in temperature and the likes of it actually performed, and it was clear that the rutting was actually coming from this section which I'm circling right now. And if we go just a little bit further, what we'll see is that actually the rut predicted was 28 millimeters and the rut measured was 32 millimeters. Using this methodology of stacking these up to, and working on the stress and a real analysis of the pavement system. Now, I think if my watch is correct, I'm probably going to be cut off shortly. You want to comment just very briefly, Buzz?
Well, we don't. We can run a few minutes over. You'll probably lose some attendees at 10 o'clock, but okay. You won't get terminated at 10 o'clock. So if anyone wants to stay on board, they can. Okay, thank you for that. I'm going to just wrap this up from my end and then open up for questions, which I've probably robbed you guys of time. But what I'm just showing in this organigram is an important one, because there are 7 parts to an MMLS test, which are depicted over here with pictures and steps that need to be taken. And I'm not going to belabor the point except to say that each of these elements has to be considered and reviewed. You've got water, you've got the ability to look in cores on the left-hand side, you've got a test bed where you can construct. So without saying much further except to say to you that what one really needs to do is apply your mind in the system, and just not, it's not just running a number and getting up a number, it's really applying engineering knowledge and getting to the end point. And that's about it. Can I stop at this point and come back to anything that anybody wants more information on, and I'm open to getting queries.
I guess, Fred, I'd like to thank you for going over it. It really is, this has been world talking. It's nice seeing the two different systems and how you're using it. It's just in that side of it that was helpful for me, so thank you.
Appreciate your comment. If there's anything that anybody wishes to touch base on that I had to go over very rapidly, we'll most likely meet each other at the international conference. We'll be talking in Washington, and my email is open to you guys to contact, or any of my colleagues who are of the users and the owners down the line. I'll gladly share that information and distribute it.
I had a question related to the, I mean, this is kind of simple, but you called RAP asphalt rubber asphalt pavement.
Yeah.
Do you use that terminology for using recycled asphalt pavement in your mix?
We in South Africa use it, but the Chinese had chosen the word RAP for rubber asphalt.
Okay. I mean, that may confuse people down the line.
Okay, I will warn them about that, and they can certainly fix that in the final paper. But just to share with you, if I take a Chinese passage, and I'm sure I've got Chinese colleagues listening down the line or maybe hearing me on this, but if you take a Chinese passage and you ask somebody to repeat this or translate this and you ask 4 people, you might just get 4 answers. So I'm just a little bit careful.
Right, I'm just trying to help out. Okay.
Thank you very much. I'll share that and take that further.
When you heat your pavements with your heaters in the system, do you have thermocouples under there and see what kind of effects you have for that heating effort?
Absolutely.
Do you get a pretty consistent heating as you would in a normal roadway?
What we do is, in fact, your point is very important. What we do is we implant thermocouples at various depths, and we monitor those, and we use for example, in the small machine, the control system is put in so that you don't overheat the surface, and that just prolongs your heating period so that you get the heat migrating and doing exactly what you're referring to. On the big machine, we've got the same thing. You've got thermocouples in there, and the whole system has got a control system so that it controls what the temperature is along the line, and it in fact makes sure that lamps are switched off where they need to be switched off to ensure that you don't overheat, or for that matter, get a profile you're looking for.
Okay, thank you.
No problem. If there's that's the, shall I say, the short and the long of it, but your point is still important to discuss in the following way. The difficulty one has is if you're out in the field with a machine, you've got the whole earth below you, so you've got to really spend time and make sure that you get the temperature in the right position. You've got to make sure that you are in an environmental condition that you're actually controlling, and that's what is made use of with the shell of the MLS. You use that as a cover to protect from environmental impact and make sure that it's cost effective and also efficient in actually getting the temperature profile you're looking for.
Thank you.
Fred, this is Buzz. I have a question. Would you expect to see a good comparison between results from the MMLS 3 and like an asphalt pavement analyzer and a Hamburg rutting test? And then would you say that the advantage of the MMLS 3 is for testing mix that's been produced through an asphalt plant and paved somewhere?
It's a double-barrel question. Let me try and answer in the following way. The fact is that perhaps let me start off by saying the MLS, which I've just shown you in the picture, has got several components that enable you both in the laboratory to produce a mix in a test bed, which if you were, for example, to just construct a test pavement, you can do the whole pavement, 1 or 2 meter long section, and replicate what you've got in the field. And we've done that in Mozambique, for example. But what I'm then saying is that the ability, and I'm now talking, obviously, if you accept the bona fides, I'm talking about the fact that you can create environmental conditions that you wish to create so that you can test them under the rolling wheel load. So the difference is such that under certain conditions you may be able to replicate something, and we've found some replication with the Hamburg test. under conditions where you are doing something that is actually also part of the, shall we say, the results of the suite of tests you've got with the MMLS. With the APA, it's a total different picture, because one of the things we have to bear in mind is that in what I slided over in the results that we had in the field, there were tests done with the HVS and also with the small, compared with the small machine. We found that there is a difference between the unidirectional testing and the bidirectional testing. So if one is trying to compare them, you've got to be very, very careful in doing that comparison. To try and come back, what I'm saying then is you've got the benefit, and I think the point you made is important. You can take the small machine. Are you still there?
You still there, Fred?
Still there?
Yeah, I don't know what's happening with that entertaining music.
Okay. Well, it says jive along. let me just try and finish.
Okay.
Are you still there?
I'm still here. Yes.
What I can say to you is that the fact is that you can do so much more analytically. If, for example, I give you the stress condition that you would have under the MLS, whether it's in the field or in the test bed, and I'll talk about the test bed in a moment, you've got a situation where you can actually do a stress analysis and come up with measurements that you can actually ratify and validate, as I indicated to you earlier on. Whereas the other two tests that you're talking to, without being derogatory about them at all, is a test which is a one-off type of application. So you've got to bear in mind that the performance you're measuring relates to that particular application. So you've got more breadth in applying it, and what we're finding is that now in South Africa with the protocol, if you look at the website, which is a Sabita website, let me just sum again, sabita.co.za. You can go in there and look at the website. There's a report to download on the protocol. But what I'm really trying to say is that it will tell you that you've actually got to take into account the temperature. You vary the temperature, you vary the tire pressure, you vary the load, and all of those aspects give you a better performance prediction. And that's just the best I can say about your question.
Okay. I appreciate the answer.
Any further questions?
I don't have any. I do need to step away now, though.
Fred,
Well,
we really appreciate you being offering to do this. I agree with Ben. This is very informative. And for everybody's benefit, the next meeting will be December the 8th, and I'll send out a reminder about that shortly. And we're looking for volunteers for December the 8th if anyone is interested.
Thank you, Buzz.
Thank you for your sharing that all with me, and for your patience, and take care of you all, and wish you well, and we'll see each other. And if there's any question, give a shoot.
Well, and Fred, before you go, I did record this presentation, and we'll have it set up so that it's linkable. And the goal with all these monthly presentations is that there's a record out there where someone can go and get a recorded stream of the presentation to get an update at a convenient time for them. So the audience eventually will be bigger than the people who participated in the meeting.
Thank you for that update, and I appreciate that. And I certainly appreciate the opportunity to make the presentation. And I hope I didn't overwhelm, or shall I say overindulge, but I thought I'd touch base and give the guidelines as to where we're heading. You
did a great job, Fred. We appreciate it, and you have a great day.
Thank you. Likewise, your end, and take care, and goodbye for now.
Bye-bye.
Bye-bye.
Thank you, gentlemen.
Bye.
Bye-bye.
Thank you, everyone.
Thank you, everybody. Bye now.